Okay, hey, this is Toby, and we're continuing with following along with the LLVM tutorial that is on LLVM.org. We completed chapter 3 last time. It was a lengthy chapter, and I had some trouble in the middle. I had to do some debugging to get past some issues. We got through that, and now we're gonna move on to chapter 4, which is about JIT and optimizer support. I really have no idea what to expect here. I have a little bit, but not a lot. I know what JIT is, but I have no idea how you would do that using LLVM. So let's look at this. So here we say, welcome to chapter 4 of the Implementing a Language with LLVM tutorial. Chapters 1 to 3 describe the implementation of a simple language and add a support for generating LLVM IR. This chapter describes 2 new techniques: adding optimizer support to your language, and adding JIT compiler support. JIT stands for just in time, which means rather than compiling your whole program into machine code, it actually defers that, delays that, and only compiles your program into machine code when you actually need to execute the code. I know the V8 JavaScript engine does this, and the Java virtual machine as well as the Smalltalk environment and a lot of other language environments nowadays do JIT. These additions will demonstrate how to get nice, efficient code for the Kaleidoscope language. Trivial constant folding. Okay, so our demonstration for chapter 3 is elegant and easy to extend. However, it does not produce wonderful code. The IRBuilder, however, does give us obvious optimizations when compiling simple code, such as if you have constants, you operate on constants, it will automatically know to pre-calculate whenever both sides of the operation are already constants. It just added the 1 and 2 and resolved it to a 3. This code is not a literal transcription of the AST built by parsing the input, because that would have been this with an add operation in the middle. Constant folding, this is called constant folding, this automatic calculation based on constants. In particular, is a very common and very important optimization, so much so that many language implementers implement constant folding support in their AST representation. With LLVM, you don't need this support in the AST, since all calls to build LLVM IR go through the LLVM IR builder. The builder itself checked to see if there was a constant folding opportunity when you call it. If so, it just does the constant fold and returns the constant instead of creating an instruction. Well, that was easy. Oh, yeah, nice. In practice, we recommend always using IRBuilder when generating code like this. It has no synthetic overhead for its use. You don't have to uglify your compiler with constant checks everywhere. I see. So like I can totally see writing a builder yourself that just generates LLVM IR code in this format yourself. But if you build it yourself, then it would not benefit from this constant folding that the IRBuilder does automatically for you, although you could implement it yourself though. So although I also probably, I have a feeling LLVM can probably also optimize this code after the fact and do the constant folding after the fact and sort of do a transform of this program. So it's saying it can dramatically reduce the amount of LLVM IR that is generated in some cases. On the other hand, the IRBuilder is limited by the fact that it does all of its analysis in line with the code as it is built. If you take a slightly more complex example, like this one, in this case, left-hand side and right-hand side of the multiplication are the same value. We'd really like to see this generate temp equals x plus 3, and then result equals temp times temp instead of computing x plus 3 twice. Unfortunately, no amount of local analysis will be able to detect and correct this. This requires two transformations: reassociation of expressions to make the adds lexically identical, and common sub-expression elimination to delete the redundant add instruction. Fortunately, LLVM provides a broad range of optimizations that you can use in the form of passes. Excuse me. I have an itch in my throat. Okay. So, alright, warning. Due to the transition to the NeoPass Manager infrastructure, this tutorial is based on LLVM Legacy Function Pass Manager, which can be found in Legacy Pass Manager. For the purpose of this tutorial, the above should be used until the Pass Manager transition is complete. Okay. We did get notified earlier on that we should be using the version of this tutorial that accompanies your version. So let me make sure my version of LLVM says the same thing, although it is just in case. Oh, not this one. Just in case the one that's public on the website is not the latest version for some reason. So we're at chapter 4. There are actually 10 chapters. Holy smokes. Okay, yep, this warning is here. So, alright. So whatever code we write here might get deprecated at some point. So LLVM provides many optimization passes which do many different sorts of things and have different trade-offs. Unlike other systems, LLVM doesn't hold the mistaken notion that one set of optimizations is right for all languages and for all situations. LLVM allows a compiler and implementer to make complete decisions about what optimizations to use, in which order, and in what situation. So these passes are basically going to take this LLVM code and transform it in some way to simplify it, remove the unnecessary bits, and optimize. Like look for opportunities where the calculations can be done in a faster way, or maybe in a more simple, or in a way that takes less steps, because that's how you get programs to go faster. So LLVM supports both whole module passes, which looks across as large of body of code as they can, often a whole file, but if run at link time, this can be a substantial portion of the whole program. It also supports and includes per function passes, which just operate on one function at a time without looking at other functions. For more information on passes and how they are run, see how to write a pass document and the list of LLVM passes. For Kaleidoscope, we're currently generating functions on the fly, one at a time, as the user types them in. We aren't shooting for the ultimate optimization experience in this setting, but we also want to catch the easy and quick stuff where possible. As such, we will choose to run a few per function optimizations as the user types the function in. If we wanted to make a static Kaleidoscope compiler, we would use exactly the code we have now, except that we would defer running the optimizer until the entire file has been parsed. In order to get per function optimizations going, we need to set up a function path manager to hold and organize the LLVM optimizations that we want to run. Once we have that, we can add a set of optimizations to run. We'll need a new function path manager for each module that we want to optimize. So we'll write a function to create and initialize both the module and the path manager for us. Okay. Wow, this is the line that initialized the module that we missed the first time around. It's gonna initialize a function path manager like that, and then this is, I think these 4 lines are like lines that adds or so registers these specific passes, and we have 4, right? So the first one is called peephole optimizations and bit twiddling optimizations. Okay, I don't know what that means. And then the next one is reassociate expressions. Yeah, all of these look very foreign to me. Simplify the control flow graph, deleting unreachable box, etc. Okay, I'm just gonna copy this. It doesn't mean a lot to me right now. Okay. Yep, I think I already said these things. Once the path manager is set up, we need to make use of it. We do this by running it after our newly created function is constructed in function ast : codegen, but before it is returned to the client. So let's go to this codegen. So function codegen. This is not function. This is prototype ast. We want the function ast codegen. It's this one. So basically, he's saying we create this. Well, we created this function, and then we add this basic block onto the function, and then work with the set the names for the arguments and so forth. Verify the function. I think it's at this point, after verifying the function, yep, we're gonna run the optimizations. Let's go do that. Yeah, what else? As you can see, this is pretty straightforward. Okay, I imagine you would need to call this initialize module and path manager function. So I will do that. So now we don't need to do this line anymore because this line has been moved over here. So I'm going to do that and recompile. Make this text a little smaller. $11 errors. Okay. Use of undeclared identifier DFPM. So I need to declare this DFPM as a static global. I will do that right after the module. There. I thought I just declared it. Oh, I did it wrong. C++ requires a type specifier for all declarations. I thought I gave. Oh. This needs to be called unique pointer, not make unique. because we're not making unique here. Okay, too few arguments to the function call. Expected 2, but we only have 1. Shoot. And no member named add in the pass manager. It looks like we're dealing with not the function pass manager, but the pass manager, which I thought is the newer version, and I'm using the legacy one right now. Okay. Are we using the legacy? Okay. I'm gonna look at the final code. We want to use the legacy pass manager. Let me go ahead and do that. I'm just gonna copy all of these includes. Oh, Kaleidoscope JIT. Okay. Not sure how to get that exactly. I'm gonna copy all of these includes here and replace these with them and see if that will help me compile it. We still have too few arguments, but now we have less errors. Run is declared in the pass manager, but I thought we were using the legacy function pass manager. That is what I thought. I'm gonna try to compile their version of the code. See if it still works. Maybe it doesn't work anymore with the new version of LLVM. You never know. Stuff go out of date all the time, you know. I'm gonna make another file. Their code 04 and build it. So I'll change this to their code 04. Their code 04. Okay, let me build. I'll just copy this line out and try to build their code this way. Well, we couldn't find that file, so that's true. Is it possible to not do the JIT parts? The JIT. Beautiful. The JIT. I'm gonna comment out the JIT parts. I'll figure out the JIT later. For now, I just want to do the optimizer bits. Making the JIT. Okay, let me try this. I still have a few places that are using the JIT, so I will, I guess, unexpected namespace name, orc. I'm gonna comment this out, maybe. the 1619. Do I still have references to the JIT? Okay, remove the last reference to the JIT. Let's see if it compiles now. Just one error. Expr symbol dot get address 615. What is this? What is this expr symbol? This is related to JIT, I think. I'm gonna ignore it for now. Handle top level expression. Okay. Evaluate it to that. Okay. There are some libraries we actually would need to link to, but it cannot find them. Interesting. Create SFG simplification pass. Create CFG simplification pass. So in order to get that, we're going to need to link to a library that does that. Let me see. I don't know if this is the end of the section on optimization, actually. And now we move on to JIT. So I would like to get this to compile, but I'm not totally sure how to do that. I think there's some libraries in here. There are some pass libraries. Maybe I need to find the specific ones and link them. So, alright, let me see. There's one called Create Reassociation Pass. There's also one called Initialize Native Target ASMParser. Oh, there's a lib LLVM ASMParser. Maybe I need to link this one. We need the native one though. Let's try linking this one. Did you just do it? I think maybe you just list that file in the command line, like here. It's just a library, so I'm gonna link it here. Clang LLVM lib, and then inside of lib I want lib LLVM what was it? ASM Parser. LLVM ASM Parser. And if nothing else, I should not see the error about ASMParser anymore if we got that right. No, I still get it. Oh, now it's no. Did I get the exact same errors as before? This is the initialize x86. Maybe I need to specifically reference the x86 version of the ASMParser. So try. There's probably an easier way to set this up, but maybe it's x86, capital X86. Yes, ASM parser. Holy moly. Okay. I think that did something. But we still don't have a reference to the printer. Okay. So I think what it is I'm gonna probably, oh my gosh. Probably need to include each of these static libraries one after another. We need the x86 ASM printer, x86 target, I guess, x86 target info, x86 target MC. I'm gonna copy these lines. And that is a lot of error. A missing V table usually means the first non-inline virtual member function has no definition. LD, symbols not found. Okay. Alright. So I'm gonna try to find the x86 ASM printer and then x86 target. I'm gonna copy this line down. Probably, I'll put this in the build file. I'm compiling their code right now. Okay. Okay. So I'm gonna go find these libraries. They start with lib LLVM, and the one I'm looking for is x86 printer. Actually don't see an x86 printer. There's an ASMParser. I mean ASM Printer. Okay, what else do I need? ASM Printer. I'm gonna need a native target. Is there something here that's called target? No, yeah. Okay. I'll copy that. Okay, I got the target Whoops. Wait, I wanna. Oh, computer is freezing up on me. Okay, I actually wanna put it in this file, this build file. Okay, there's the LLVM LLVM target. Do we have another one? Target info initialize. Okay, we probably already have it with the target one. Okay, I'm gonna try to run this build file. Nope, still a lot of errors. Oh, now it's the native Target ASM printer. The x86 ASM printer, but does that even exist? Well, I also did I put the printer in here? I put the parser. I put two parsers in here. Did I ever put the printer in here? Oh, I did put this printer here. Is there a there's only one ASM printer, and I have included it. Well, we also have some stuff in Clang and CMake, but I'm not sure if that's what I need. I did read something that said something like, it's better if you have your project set up as a sibling directory of the LLVM project, and sort of set up the references over to the sources in the LLVM project. I'm afraid though that kind of setup might need me to compile the LLVM project, which last time I was not able to do. But if this doesn't work, I might need to look harder at that. There's actually WebAssembly is one of the targets. Okay, let me think. Okay, I'm gonna cut this video short then, and try to think of some ideas of how to overcome this hurdle of compiling this stuff. Yeah, once I figure that out, I will present you with more content.